So today we'll talk about something similar to all this network flows theory, but slightly different. So we'll talk about global cut problem. So what is this problem about? You have a graph. Let's say you have a graph, and let's say each node has some cost, or each edge. So you have some graph. Let's say something like this. And there is a cost for each edge. Let's say something like 3, 6, 5. Let's say 1 and 3 and 7, something like that. And the problem is to find the set of edges. So if you remove these edges from the graph will be no longer connected. So you want to break the connectivity of this graph. Right now the graph is connected, but you want to remove some edges of the graph, so the graph became not connected. For example, in this graph you can remove these two edges. Yeah? So if you remove these two edges, the graph will be no longer connected, right? So we want to find the cut of the minimal total cost of all the edges. Minimal sum of all costs. Let's see. Let's see. Let's see the weight of the graph, the weight of the edges instead of the cost of the edge. Yeah? So we want to remove the edges of the minimal total weight. Let's say minimal total weight. Such if we remove all this. See. So if we remove these edges, all edges from this cut, graph is not connected. Graph is not connected. Something like that. Why is it different from the normal minimal cut problem? We've already discussed minimal cut problem when we talk about flows, right? The difference is in normal minimal cut problem, you want to break connectivity between two given nodes. So you have two given nodes S and T, and you want to break connectivity between these nodes. So you want to remove some edges of your graph. So these two nodes are no longer connected. So you need to break this like this and remove all edges in this area, right? So that's the minimal cut problem we discussed in the lectures when we talk about maximal flows. And now we just want to break the connectivity of the graph. So we don't have any specific nodes S and T. We just want to remove some set of edges, so the graph will be not connected. So that's the difference. Well, first of all, let's prove this problem is actually can be solved in polynomial time. Can you find any polynomial time solution for this problem? So again, what I want to do, I have a graph. I want to remove some set of edges, so there will be two different connected components, or maybe not two, maybe more. Two minimal cut for all pair of nodes. Yeah, makes sense. Yes. So we know how to find the minimal cut between two specific nodes. So we can iterate for all possible pairs of nodes and find the minimal cut between these. So we'll iterate for all S from 1 to N, iterate for all T from, let's say, S plus 1 to N, and try to find the minimal cut between these ones. So we will just update the result with a minimal cut between S and T. Minimal cut between S and T. No, we cannot simply reduce the problem to minimal cut problem, because we kind of want to find specific nodes S and T, right? So you cannot just put all like make all the nodes S and make all the nodes T, because you want to find, the problem is you want to find the maximal flow between two specific nodes, right? So what will be time complexity? What will be time complexity here? So we have these two loops. These two loops work in n square iterations, and here we just use the maximal flow algorithm to find this minimal cut. Let's say so multiplied by the time, let's say flow. So this is the time complexity of the maximal flow algorithm. So we discussed many different maximal flow algorithms. They have different time complexity. So let's say something like NM, something like, yeah, maybe. There are different maximal flow algorithms for different situations. So, okay. Again, it depends. If your graph has unit, if all weights of the edges are just ones, so if we have one for each of the weights, so maximal flow can be far faster than in n time. Yeah? So the stack complexity depends actually on the structure of your graph. Let's improve this algorithm. We can improve it using a very simple trick. We can remove one of these ends. Can you see how can we do it? So by right now we call this minimal cut subroutine n squared times. We can actually call it not n squared times, but right, just n times. Can you see how can we improve it? Again, in this algorithm, we try to select all possible pairs of nodes. Yeah. So if one node, so there is some minimal cut. There is some minimal cut. We want to iterate all. So if we remove all edges from this minimal cut, the graph will be split into two connected components. So we try to find some node in this connected component S and some node in this connected component. So in the graph, there always, if you select some global cut, there will be some connected components. So we try to find two nodes which will belong to different connected components if we select this minimal cut. If we iterate all possible pairs, then at least for one pair, we will pick two nodes in different connected components. So there is some global cut, and for this minimal global cut, at least one of these pairs will have two nodes in different connected components. It's pretty kind of no. If you just make what you want to do, yeah, in your suggestion, you want to make specific node T and just connect it. So if you do it like this, you will find something strange. So you want to break connectivity between node S and this node T. That's not what you want to do. Even if you make all these nodes of infinite capacity, you will find something strange. For example, let me think. Just because that's not what you want to find. So you want to find the cut between this set of nodes and this set of nodes, and you also have this. No, yes, if you add all the edges of infinite capacity, the minimal cut will always be just to remove all nodes connected to S, or all the edges connected to S. Because if you, so there's node S, yeah. If you don't remove these edges, then you will have path like this. And this edge has infinite capacity, so you need to remove all these edges. Yeah, makes sense. So the problem can be solved with a single run of maximal flow algorithm, unfortunately. but it can be solved in n runs of maximal flow algorithm. Again, the idea is very simple. We don't need to check all possible pairs. We just need to check all pairs from node 1 to all other nodes. Because let's take a look at node 1. There is node number 1. It is somewhere in the graph. So let's say this node has index 1. Yeah. This first node belongs to some connect component after we apply this minimal cut. Yeah. So after we apply minimal cut, with node 1 will belong to some connect component. We can use this node as node S and only iterate or not all possible nodes T. So we'll check only pairs from node 1 to all other nodes. Again, node 1 belongs to some connect component. We'll try to find the node which belongs to different connect component. So iterate on all possible nodes. At least one of them will belong to different connect component after we apply this minimal global cut. So we check all these pairs and find the minimal result. That's all. And time complexity will be improved like this. Ta-da! That's the first algorithm. So again, this is some polynomial algorithm. Now we'll try to make better polynomial algorithm. Let's go. So let's do the following thing. Let's try it from different angle. So let's take the graph. And if we have more than 2 nodes in the graph, more than 3 nodes actually. Yeah, more than at least 2. Yeah. If we have at least 2 nodes in the graph, let's pick 2 random nodes in the graph. Some nodes. Let's pick 2 different nodes, just randomly, and try to look at this node. So you have 2 nodes of your graph. These nodes in the final cut, they belong to the same connect component or to different connect components. If they belong to different connect components, then you can just find the minimal cut between these 2 nodes and update your result. Yeah. So if these nodes S and T belong to different connect component, then we'll just find the minimal cut between these 2 nodes and update the result. Let's update the result. Now, again, if S and T belong to different connect components, then we found the result. What if not? What if we select some 2 nodes and they belong to the same connect component? Then what we can do is to merge these 2 nodes into a single node. Again, because if they belong to the same component, we can track them as a single node. Yeah, we can put both these S and T in one connect component or to another connect component. So if they belong to the same connect component, we can remove these 2 nodes and replace them with a single node with same set of edges. Okay? Let's say it's merge. Well, let's try, for example, for this graph. What will happen? Let's put some indices here just to make it. So 1, 2, 3, 4, and 5. how do we merge? We just merge two nodes into one node and make all the same edges, just concatenate all the list of edges from these both nodes into one. So I'll show you. So we pick two random nodes. For example, nodes 1 and 3. This is S and this is T. Now, we try to find the minimal cut between S and T. Minimal cut between S and T equal to 9, right? So we can put 6 here plus 3 here. So minimal cut here will be 9. And now we merge these two nodes into single node. So we have this single node 1 and 3, and all these nodes here as well. Now we have this edge 3 and edge 5. We'll have some parallel edges, that's fine. We can replace parallel edges with a single edge like we did in minimal cut, but it's not important. 3, 7, and 1. Now again, you select two random nodes. Let's say we pick this S and this T. Find the minimal cut between these two nodes. It will be 4, right? And then merge them. So we merge nodes 2 and 5, and here we have 1 and 3, and here we have 4. And we have edges 3, 5, and 3 again, and we have edges 1 and 7. And just continue until you have only a single node. So now you select, let's see, S and T. Again, minimal cut will be 8. And again, you merge them. You have 2, 4, and 5, and here you have 1 and 3, and many edges 3, 5, and 3. Now again, you select S and T, and cut is 11. Okay. And now you simply take the minimum of all these values. So minimum will be here. That's all. That's how we do it. Yeah. So you start from your graph, select two random nodes, find the minimal cut between these two nodes, and then merge them into one. Then again, select two random nodes, find minimal cut, merge them into one, and so on. In the end, you will have only single node. And now you just take minimum of all these minimal cuts. It will be the minimal global cut. Makes sense. Okay. Good. What is the time complexity of this algorithm? Why does this work? Okay, I thought I explained it. Okay. Why does it work? Because we tried all possible ways of building a global cut. Again, each time we take two nodes, and these nodes, let's look at the global cut. So there is some global cut, yeah? So there is some global cut. We don't know what is the global cut, but there is some. So this is the minimal cut. We don't know what is it, but there is some global cut. Yeah? Now, if you pick two random nodes, they may belong to the same connect component or to different connect components. If they belong to different components, so if you pick two random nodes and one of them is here, one of them is here, then you will find the minimal cut and you will just find your result. Yeah. So if you picked two nodes from different components, then here you will just find the minimal global cut. And if you pick the nodes from the same connect components, Then you can sorry, my chat is not working. Then they act like a single node. So they belong to this connected component or this connected component. So instead of thinking of them as two separate nodes, we will just think about them as one node. Yeah. Again, a node is something that we can put into one connected component or another connected component. Yeah? If these two nodes belong to the same connected component, they basically act like a single node. We can put them both here, or we can put them both here. So we can merge them into single node and solve the same problem for the compressed graph. Again, let's do it once again. So let's look at this graph. We have these nodes S and T. If they belong to different connected components, then we will find the result just by using this minimal cut subroutine. Yeah? And if they belong to the same connected component, then the minimal cut in this graph is the same as minimal cut in this graph. Because let's look at this graph. We have some minimal cut in this graph. We will just uncompress this node 1 and 3 and have the minimal cut for this graph. Clear enough? No? Yes. If two nodes belong to the same connected components, merging them will not affect the minimal cut. Because minimal cut do not contain any nodes between them. Yeah. Okay, nice. So what's time complexity of this algorithm? No, let's think. So we have up to n iterations of this loop, right? So we have n iterations of this loop because each time we decrease the number of nodes. Each time we calculate the minimal cut, again using maximal flow algorithm, and we merge some nodes. What is time complexity of merging the nodes? No, I claim it's not that big. So time complexity of merging nodes is no more than m, let's say. So time complexity of finding the minimal flow. So here we call the maximal flow algorithm, and here we merging some nodes. We can do it easily just by constructing the whole graph. We can construct the whole graph from this graph in linear time. Okay, so let's say time m. We can actually do it faster. If you think about it, what we need to do when we merge two nodes into one, we can just take these nodes, take the list of the edges, concatenate this list into a single list, and just remove two nodes and add a single. So again, how to merge two nodes? You remove these two nodes from the graph and insert a new node with the same edge list as a union of these two sets. You can do it actually in time n. It's basically removing edge or removing the node or adding the node, actually done in linear time. You add the node and all outgoing edges. There may be up to n outgoing edges, so the time complexity will be n. Yeah. So time complexity is basically degree of these nodes. Maximal degree is n. So there may be no more than n edges. Well, we have some parallel edges, but it actually doesn't matter. Okay. But for this algorithm, it's not important. It will be important later, but not it. So now, the bottleneck of this algorithm is actually this maximal flow. Yeah. So time complexity will be, again, it will be n multiplied by flow plus n, something like that. Okay, let's say plus m, just for simplicity. Okay, I'll just leave it. You can do it in time n. It's a little bit more complicated than just rebuilding the whole graph, but it's doable. But again, in this pair, flow is much slower than this linear time complexity. So actually, the time complexity is the same as for this algorithm. So we got different algorithm, but the same time complexity. Same time complexity for this algorithm in this algorithm is basically the same. But this algorithm can be improved. How can we improve this algorithm? We will improve it by speeding up this part. So we will speed up, we will do the same thing as here, but without this maximal flow algorithm. How can we do it? Let's see. What we're doing here, we try to find some random nodes and the minimal cut between them. But we can select any pair of nodes. So we will build another algorithm, which will allow the algorithm to select the pair of nodes. Usually, in the maximal flow algorithm, you're given some node S and some node T, and you want to find the minimal cut between S and T. But we will build another algorithm. We will give the algorithm some graph, and the algorithm will select some nodes S and T and find the minimal cut between these nodes S and T. And maybe it will be easier because, again, the graph can pick some good nodes. So for some good nodes, they may be easier to find the minimal cut. Okay, let's write it here. Once again, so what's happening in this minimal cut subroutine? We take some graph G and some nodes S and T and receive the minimal cut. That's how the usual maximal flow algorithm works. But we want something different. We want for graph G, find some nodes S and T and minimal cut between them. And this problem is actually easier. So again, our algorithm can pick some good nodes S and T and find the cut between these two good nodes. And it will be easier then to find the minimal cut between two specific nodes. Let's go. So this algorithm is called Stoer-Wagner algorithm. It works like magic. Absolutely magical algorithm. So what we'll do, we will try to construct the following thing. We will, let me write it here. We will mark some nodes in specific order. Let's start from any node. Let's take any node of the graph and mark it. Let's put it here. So first we select node 1. Now, each time we will mark a node which has the maximal total weight of the edges from this node to all the previously marked nodes. What does it mean? Let's look at all unmarked nodes. For each node, we will calculate the total sum of weights of all the edges from this node to all previously marked nodes. For example, look, here we have for this node, this sum is 6. For this node, this sum is 3. For these two is 0. So we select the node which has the maximal total sum of these weights. In our case, it's node 3. So for node 3, this sum is 6. It's maximal possible, so we mark this node and put it here. No, it's 3. Now again, from all nodes, we select a node which has the maximal possible connectivity to all total weight of the edges from this node to all previously marked nodes. So for this node, the sum is 3. For this node is 0. For this node is 3 plus 5. So this node has maximal total weight of the edges. So we select this node 2, mark it, and put it here. And so on. Now we have, for this node we have 3, for this node we have 1. This is maximal possible, mark this 5, put it here. And finally here we have node 4, mark it, put it here. It can be also yes. Each time we select some node which is a neighbor of the previously marked nodes and has the maximal total sum of the edges to the previously marked nodes. So let's write it like here. Let's remove it. Let's remove it. It's interesting anymore. So at any point we have some set of the marked nodes. So let's say, let's call it set A. So set A connect all the marked nodes of our graph. We select node V. Look at everything, all the edges from V to this set A. Let's call it the weight of V to A. Is just the sum of all weights VU, U belong to A. Yeah. So it's sum of all these nodes. Now each time we do the following. We select the node with maximal sum. VA is maximal and add it to node, add it to V, like this. So we find the node with maximal sum and mark it and also put it in the set A. Now what's next? How does it actually connect it to all the problem? Yeah. Right now it doesn't look like the minimal cut problem at all, but now it's magic. The magic works like this. Let's pick two last nodes in this order. So let's say this node is S, this node is T. Now I simply prove that the mean cut between S and T is basically equal to the sum of all the edges connected to S. SV. Again, let's see it here. So we have this node S, this is node T. I claim that the minimal cut between S and T is basically just to remove all the edges connected to S. So minimal cut between these two nodes just contains these two edges. So for this graph it's true. Yeah. So minimal cut between here and here is 8. Magic. Just say it's clear enough, if it's clear enough, or if you have any questions, just ask them. I need to have some feedback that it's clear, because it's like these algorithms are quite magical. So at some point you may lose the how it's called. So okay, let's go next. This step we select the maximal, so we're left that the node gives me. No, it's not the minimal cut. It's not the minimal global cut. It is a minimal cut between some nodes. So I claim that this sum is the minimal cut between nodes S and T. So if I pick two last nodes in this order, so I add the nodes one by one to this set A. I select two nodes which was added the last to this set. And I claim that the maximal cut, minimal cut between these two nodes is easily calculated. So to calculate the minimal cut between S and T, these two last nodes, you just need to cut all the edges connected to S. That's not the minimal global cut. It's just minimal cut between these two nodes. And after this, I will apply the same loop like before. So I can take this minimal cut between S and T, update my result, and then merge them and continue. So I do it, merge them, do it again, merge, and so on until I have a single node. Yeah. Let's prove it. Let's prove it. Let's go. So we have some nodes here. So last two nodes are S and T. Let's look at the minimal cut between S and T. So there is some minimal cut, yes? So for these nodes S and T, there is some minimal cut. Let's say it's C. So let's say C is the minimal cut between S and T. Yeah? So let's draw it like this. So this is the minimal cut. So above this line is the first connected component, below is the second connected component. Yeah? So this node S belongs to this connected component, node T belongs to this connected component. Let's look at all the previous nodes in this order. So again, I draw these nodes in the order I select them here. Yeah? So I go from left to right, add the nodes to my set A. So I have something, let's say something here, something here, something here, something here. So again, what this picture says, so from left to right is the order in which I added these nodes to my set A. So if I pick the first node, then each time I pick the node which is mostly connected to the previous connector. Now, above this line is the first set, below this line is the second set. Again, that's this cut between S and T split all the nodes into two sets, like one connected component and non-connected component. Yeah? So S belongs to this connected component, T belongs to this connected component. Now, let's go in this order and mark every node such that the previous node belongs to different connected components. So we'll mark, we have this series, right? So for each series, we just pick the first node in this series. Chuk, 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 and chuk. So I just selected the first node in this series. So I select the node if the next node belongs to the same connected component. No. If the previous node belongs to different connected component. Yeah. Nice. That's almost all. That's almost it. Now, I will prove the simple theorem. Let's pick some interesting, so let's call it interesting node. Let's pick some interesting node here. It's node V. Let's look at two values. The first value is the sum of all weights from node V to all previous nodes, like the same weight as here. So let's say okay, let's draw it here. So let's say set AV is the set of all nodes to the left from V. So this set of nodes we will call AV. Yeah? Now let's look at the value of W from V to AV. So it is the sum of weights of all edges from this node V to all previous nodes. Like the same sum as here, the sum which we minimize is here. Second thing, let's look at the all edges belong to this part of the graph, including V, such that they belong to my minimal cut. Let's see. So CV will be total weight of edges such that this edge belong to the cut, belong to C. And both ends are, both ends and that's less or equal than B. So we remove all these nodes and look at all the edges in this area. And the total weight of all these edges is CV. Let me draw some picture here. So I have this node V. So this first thing is the sum of everything connected to V. So we have edges like this, and we have edges like this. So this is weight of everything from V to A. Yep. So this thing is the total weight of all edges from V to everything to the left. And now the second thing is we have this node V and everything, let's say everything here. Second thing, this thing, is total weight of all edges which belong to your cut and connect the nodes to the left from V, including B. So we have edges like this and something here. Yeah. So this is CV. Yeah. Clear enough? So this thing is sum of all these edges, total weight of all these edges. And this thing is the total weight of these edges. Now a simple theorem. This thing is less or equal than this thing. So weight of V to AV is less or equal than the weight of CV. Ta-da! Let's prove it. Let's prove this theorem. So let's take the node V and look at this thing. So this thing is total weight of all the edges connected to node V. Let's look at the previous interesting nodes, this node. So this node, let's say it's U. Let's look everything before this U and this. Now here, I want to calculate total weight of all the edges from V to everything to the left. Let's split it into two things. So I want to have weight of everything connected to AU, so to everything before U, yeah, to this part, plus the weight of everything from V to everything like from U to V minus 1. So I want to calculate total weight of all the edges from V to everything to the left. These edges may go here or they may go here. So I just split the sum into two sums. You're too quiet, say something. Sometimes I'm afraid my stream is not working. Can you just say you're still here, okay? Just do not make me nervous, okay? Now, let's look at these two sums. So let's look at this thing. What can we say about the total weight of edges from V to everything here? We can say actually a very simple thing. So total weight of these edges is less or equal than total weight of edges from U to set AU. Why is it true? No, because each time we select the node with maximal sum. So when we picked this node U, we picked node U instead of V, because the sum for node U was greater or equal than sum for. So this node U has maximal sum. So the same sum for node V must be less or equal than this sum. And this thing, by just as we just proved by induction from left to right, and this sum is less or equal than CU. Because this is also some interesting note. For this interest node, we already proved that sum for this node is less or equal than CU. And now we have following thing. We have CU plus weight of these edges. And I claim that all of these edges belong to the cut CV. No, because again, here I have edges in CU. Edges in CU are all these edges, right? And edges from V to this thing is set of these edges. Now, all these edges belong to set CV. So the sum of these two sets is sum of these two sets is less or equal than the set CV. Again, set CV contains all the edges in this area which belong to your card. So these edges belongs to CV, these edges belong to CV. So the total weight of these edges is not greater than CV. That's all. That's the whole proof. Very simple, actually. Now I just claim that this theorem actually proves what we need to hear. So, why this is true? Can you see it? So I claim if we prove this theorem, we actually prove that the algorithm is working. Why is it true again? Because node S is interesting. Because the previous node is T, S and T belong to different connected components. So node S is interesting. So for this node S, we know that the weight of this minimal cut is greater or equal than the sum of everything which goes out of this node P, S. But if we cut everything from node S, it is some cut. So we know that we have cut of this size, and we know that all other cuts are greater or equal than this cut. So this cut must be a minimal cut. Connect everything to S. We can just connect everything to S and get a smaller cut. Yeah, that's also true. But basically, what we have here is there may be some cuts of the same of the same weight. Yeah. Yeah. So the cut which just contains all the edges connected to S is the minimal cut. There may be some other cut which has the same weight, but they may not have a cut which is smaller than this cut, because any other cut will be greater or equal than our cut. That's all. That's Stoer-Wagner algorithm. Now let's calculate time complexity. What is time complexity of this algorithm? In time complexity, what we need to do? We need to find the node with minimal sum, and then when we put this V to the set A, we need to update everything connected to V. So we need some data structure which can find the maximal value and can update the values. We can use a heap, for example. If you just use binary heap, you will have time complexity m log n. If you use Fibonacci heap, you will have m plus n log n. Not that important, but you may do. So what is total time complexity? Well, again, we have this outer loop from the previous algorithm. So each time we run all this routine, and then we merge S and T into one node. Yeah? So we do it n times. Each time we do all this thing, which is running time is m log n, let's say. Again, it's for binary heaps. If you use Fibonacci heap, it will be something like nm plus n square log n. Yeah? Nice. Now we'll do something more interesting. Now we'll discuss another algorithm which actually works faster, but it is randomized. So it's one of the problems when we have randomized algorithms which actually works faster than determined algorithm. Whew, let's go. So the next algorithm we'll discuss is Karger algorithm. Very simple algorithm. Let's run it on a. Let's have a graph without weights. Let's have all weights equal to 1, just for simplicity. We will improve it for the weighted graph, but right now let's have some unweighted graph. So we have some unweighted graph, and you want to find the minimal cut in this graph. So you just want to find the minimal number of edges you need to remove. How can you do it? We'll do it in a very cool way. Let's pick a random edge. We have some edges. Let's select a random edge. For example, let's say this edge. No, let's look at this edge. So this edge connects some two nodes. No, these two nodes look like they are connected to each other. Yeah, so they most likely belong to the same connected component, right? Yeah. So let's pick random edge. Look at two ends of this edge. They most likely belong to the same connected component. So let's not run this maximal flow algorithm. Let's just merge them. Let's just guess. So my guess is if we pick some random edge, it most likely connects some nodes from the same connected component. So we'll just guess that these two nodes belong to the same connected components. We don't run all these routines to actually calculate the maximal flow. We just guess that they belong to the same connected component. And we merge them. Let's merge them. We have 3 and 5. 1, 2, and 4. We have 3 and 5 here. Oh, like this, right? Now again, let's pick some random edge. Let's pick, I don't know, this edge. Looks very random. Pick the random edge. And then just guess that you need some belief in this. So let's just believe that these two nodes belong to the same connected component. If they belong to the same connected component, we can just merge them. Yeah, just merge these two nodes. So I merge them. I have nodes 1, 2, and 3, 4, 5 here. Now I have two edges between 2 and 3, 4, 5. I will have some parallel edges, so that's fine. And now again, you have some graph. Let's pick some random nodes, random edge. And just merge these two into one. Now, when you have only two nodes, it's easy to find the minimal cut. So for this graph, minimal cut is 3. Ta-da! Very easy. That's the whole algorithm. Again, we start from this graph. Each time we pick some random edge, and we merge the nodes of this edge, and continue until we have only two nodes. When we have only two nodes, we can simply calculate the minimal cut just by counting number of edges between these two nodes. That's all. What is the time complexity of this algorithm? No, I claim you can do it in n² time. So in n² time, you can compress everything. Okay? Like n times you compress two nodes into one, you can do it in linear time. Yeah. So time complexity is n². What's the problem here? Problem is that sometimes we actually guess wrong. Yeah. For example, in this case, we say that minimal cut is 3, but it is actually 2. So sometimes we just return the wrong result. Can we do something about it? Let's calculate the probability. Let's calculate the probability that we will pick the good result. Yeah, it's called the Monte Carlo algorithm again. So this algorithm sometimes gives you the bad result. Yeah, that's different from the randomized algorithm we discussed before. So we discussed some randomized algorithm before, but for example, in quicksort algorithm, in some data structures like in trips, we use some randomness. But before we had algorithms which are correct always, but the time complexity is the random value, right? Here it is different. Here the time complexity is always n². So, but the result is random. So sometimes the result is wrong. Actually, the sad thing is we actually don't know if the result is wrong or so. So the algorithm returns you result 3. We cannot check that it is correct. It's this kind of strange feeling that when you call algorithm, it will return you some result and you don't know if this result is correct or not. Let's calculate the probability. Let's calculate the probability that the result is probability of success. Success. Let's calculate the probability that that this algorithm will actually find the minimal cut. How to calculate probability? Let's see what can go wrong when we get the wrong result. We get the wrong result when we pick one of the edges from the minimal cut. Yeah. So what was our guess? So we pick some random edge, and we guess that this edge is not in the minimal cut. So the problem is when we pick some random edge, and this edge actually belongs to your minimal cut. So what is the probability that your random edge belongs to some minimal cut? Some random here belongs to C. Let's see this random. Okay, like this. So you pick some random edge. What is the probability that this edge belongs to the minimal cut? We will bound it like this. So let's bound the value of the minimal cut. I claim that the minimal cut is not greater than the minimal degree of the node. That's true, right? Because if you have some node with degree, we can just remove all the edges connected to this node and have some cut. So minimal cut is no more than the minimal degree of the node. And the minimal degree of the node can be bound very easily. So the minimal degree is not greater than the average degree. The average degree of the nodes is 2m over m. Yep. Yes, for example, if you have a full graph, then you have two n square here and 2 n here. We have n square over 2 here, so it will be n square over n. So the size of the minimal cut in the full graph is n. Yes. If you have a sparse graph, then the minimal cut is small. For example, in planar graph, you can always cut some 5 edges to make it not connected. So again, the minimal cut is not greater than the minimal degree, because you can take this node with minimal degree and cut all the edges connected to this node. Minimal degree is not greater than the average degree. Average degree is thus sum of all degrees. Sum of all degrees is 2m, because every edge increases degrees by 1. Yeah? So it's 2m divided by the number of nodes. So this is the average degree. Minimal degree is not greater than the average degree. So the size of minimal cut is not greater than 2m over n. Now we pick a random edge. So there are m possible edges. So what is the probability that we will pick one of these edges? It is no more than size of minimal cut divided by the total number of edges. So the probability that the random edge will belong to minimal cut is no more than 2m over n divided by m, right? It is 2 over m. So this is the probability that we will pick the wrong edge. But we do it not once, we do it multiple times. Yeah? So we need to find the probability that each time we select a good edge. So this is probability that we select the bad edge. What will be the probability to select a good edge? No, it will be 1 minus this. So in the first step, we pick some random edge. What is the probability that we pick a good edge? It will be n minus 2 over n, right? It's 1 minus this. So this is the probability that in the first step we pick the good edge. Now in the second step here, the size of graph is n minus 1. So the probability that we'll pick a good edge will be n minus 3 over n minus 1. Okay? So in the second step, we select a good edge with probability n minus 3 or n minus 1. Then it will be n minus 4 or n minus 2, and so on. In the end, it will be something like 2 over 4 and 1 over 3. So this is the probability that in each step we will select some good edge. Now let's just multiply all this. So in this formula we can eliminate this n minus 2 and this n minus 2, this n minus 3 and this n minus 3, and so on. So we can eliminate everything except these 4 elements. It will be 2 over n minus 1. So it's about 1 over n. The probability is quite small. Yeah. So for big graph, the probability that we will pick good edges all the way is quite small. Yeah, it's just 1 over n squared. But what can we do? If you have some algorithm which works correctly but with small probability, we can just run it multiple times. If we run the same algorithm multiple times, the probability will be increasing, right? So, how many times should we run this algorithm to have some good probability of success? Have any intuition about this? N squared, right? So we can run this same algorithm n squared times. Just the same thing. And just hope that at least once we will succeed. What is the probability? So we run the same algorithm n squared times. What will be the probability? Probability is like this. What's the probability of success? will be, again, the probability is 1 minus the probability of failure. So it will be 1 minus the probability of failure. Probability of failure will be that we failed 1 minus minus 1. Probability of one failure, and we need to fail all n squared times. Again, this is probability of one failure. This is probability of n square failures, right? So we need to have at least one success. So this is a probability of having at least one success. Now this thing is actually about 1 over e. So probability of success will be something like 1 minus 1 over e. So now this probability not depend on this n. So probability is the same. It's not perfect, but it's something, yeah? So we have some constant probability of success. Now what can we do? We can run it not n squared times, but multiple of n squared. So we can not run not n squared time, but let's say n squared multiplied by k. If we run k n squared time, the probability of failure here will be not 1 over e, but 1 over e power k. Like this. And now we can we can actually control the probability of failure. Yeah. So if we want probability to be, let's say, 1 over million cases, we can select k as logarithm of million and run it that many times. If you want probability to be 1 in billion cases, you can select k as logarithm of billion and so on. So just by controlling this k, you can control the probability of the failure of this algorithm. That's all. So again, what is total time complexity? Total time complexity will be something like that. So we run it at n squared time. Now we run the whole n square algorithm n squared times. So it will be n power 4. And then we just run it until we get the good probability. So it will be multiplied by log of 1 over epsilon, let's say, something like that. So if epsilon is the desired probability of success. Something like that. Yeah, you may think about geometric distribution as well. Yeah, it's just the same thing, but no, here I kind of cheated a little bit. So I go from here to here somehow. No, it's good. It's just a good intuition behind this, but you can do it more carefully, yes, but it's a little bit more cheater way to do it. Go. Now, what's next? We can improve this algorithm. So this is Karger algorithm, classical Karger algorithm. But then there's another guy, Karger-Stein, right? Karger-Stein, right? Stein, right? So then we improve this algorithm. Very interesting way. Let's do it. So we can do the same algorithm, but with better time complexity. What's the idea? The idea is to improve actually this probability. So right now the probability of success is pretty small. So we need to run this algorithm n squared times. Let's try to improve this probability. So we'll try to make the same thing, but with better probability of success. Let's go. So let's start from the, again, you have graph of size n. Yeah. Now you select some random edge. merge these two nodes into one. And you have graph of size n minus 1. Again, you select random edge. You get graph of n minus 2. And so on. Now, let's stop at some point. So before we just did it until we get the graph of size 1. Let's stop at some point. Let's stop at some point so that the probability of success will be about 1 over 2. So let's see. So how many steps can we do until the probability is about 1/2, about 50%? So I want to have about 50 probability of success. So how many steps can I do? Again, let's look. Let's take so this is the probability of success. So if we stop at point, let's say k. So in that we have graph of size k. This is k minus 2, k plus 1, k minus 1, right? So the probability will be something like it's about, let's say, about k square over n square, right? And I want it to be 1 over 2. What is k? Okay. Very simple task, right? So I want to make these steps until the probability of success will be 1 over 2. How many steps can I make? Ta-da! This problem. Can you find the value of k from this formula? Okay, so it's easy. Yes, k must be about n over square root of n, or square root of 2. Right. So I can make these steps until I have the graph of the size n over square root of 2. Now the interesting thing. Starting from this point, I will do the same algorithm, but I will do it twice. So I will call 2 independent subroutines of the same algorithm and find the minimal result. So I will make one branch and another branch. So I will just do all the same thing twice and get the minimum of these two results. So each of these subroutines will do the same steps until you have graph of size n over 2, right? And then again, here and here, I will make two different calls of the same algorithm. So I'll have and so on. So again, the algorithm works like this. You have graph of size n. You compress it until you have graph of size n over square root of 2. And from this small graph, you call the same algorithm twice. So the same algorithm will compress your graph to the size n over 2, because n over square root of n, square root of 2 over square root of 2 is n over 2, right? So you compress graph until you have graph of n over 2, and then again call the same algorithm twice, and so on. So you have like exponential number of branches in this graph. It's like a binary tree of, like, we'll calculate the height of this graph. Again, if probability of success in any branch is actually 1/2. So in all these branches, probability is about 50%. And so on in each of these. So each of these branches has probability of 50% of success. Yeah, now first let's talk about time complexity. What is the time complexity of this algorithm? Well, let's see. We need to calculate time complexity for graph n. What is the time complexity? We need to make all these steps, right? So we make all these steps in time n squared. So time n squared is time for this part. And now we call the same algorithm twice. So we twice call the algorithm on the graph of size n or square root of 2. Can you solve this? We discussed recursions like this in the first semester, if you remember. Yeah, it was a long time ago. Can you get the time complexity from this recurrent formula? Yeah, it was a long time ago. Okay, if you don't remember, it's like a special master theorem. It's called master theorem. We can do it in just basically. Yeah, you can use master theorem to calculate some complexity. If you remember how it's working. Okay, I'll just explain it just in very simple way. So for this branch, time complexity is n squared, right? For these two branches, time complexity is n squared from n over. So we need to take n over square root of 2, and then take square of this. So time complexity of this branch is n squared over 2. And for this branch, it's also n squared over 2. So we make two branches. Each branch has time complexity n squared over 2. Now here we have 4 branches. And all of these 4 branches has time complexity n squared over 4. So time complexity here is n squared. Sum of this complexity is n squared. Sum of these 4 complexities is also n squared. So in each layer, total time complexity is n squared. Now we just need to calculate number of layers. Number of layers is log n. Yeah. So we have log n layers, and in each layer, total time complexity is n squared. So that complexity here is actually n squared log n. Yeah. Okay, so that's the yes, very trivial case for master theorem. This is actually a case when basically what you want to calculate the logarithm of 2 base square root of 2. It will be 2, and this exponent is the same as this exponent. So you have n squared here and n squared here. So this n squared will be multiplied by a number of layers. It basically means that in each layer you decrease problem in such a way that this complexity is the same. If it is smaller than this, then it will be exponential decrease in sum. If it is greater, then this will be much better than this. But if it is the same, then you have just log n layers, and each layer you have n squared. Yeah. Good. So this is time complexity. Now, what about the probability? So I just note that it is actually not that slower than the previous algorithm. Our previous algorithm worked in n squared time. This is just n squared log n, so it's almost the same time complexity as the previous algorithm. But what about probability of success? I claim that probability of success is small, or is large, much larger than this before. Okay, that's the final thing we want to prove. I want to prove that the probability of success is actually 1 divided by log n. Well, okay. Let's see now. Okay. I don't want to make big O in probabilities. What I will prove? I will prove it by induction. So I will prove that the probability of success is something like that. I will prove it is greater or equal than 1 over log, let's say base square root of n. So since we have this logarithm base square root of 2, I'll prove it like this. Proved by induction. So let's do it like this. So how this probability is calculated? So it's calculated like this. What is the probability of success? Well, first of all, I need to calculate. I need to calculate here everything correctly. So my probability of success is calculated like this. First, I need to make all these steps correctly. The probability of making these steps correctly is 50%. Right? Yeah. Now, I have these two branches. I need to have success in at least one of these branches. Yeah. So what is the probability of having at least one success here or here? Let's say P of n. P of n is 1 over 2 multiplied by probability of having at least one success. So what's probability of having at least one success? It's 1 minus probability of having two failures. Yeah. What is probability of having both these branches wrong? It is 1 minus p of n over square root of 2. This probability of one failure, we just make square of this. This is probability of two failures. This is 1 minus probability of two failures. Is probability of at least one success. Right? Again, this is probability of success in this branch. Now, this 1 minus this is probability of failure in this branch. Now we make it square because we have two branches. We need to fail in both these branches. So this is probability of having failure in both these branches. Now 1 minus this is probability of not having two failures. So it's basically of having at least one success. And this 50% is just because we have here, we have probability of 50%. No, let's do it. So what? Let's just prove it. Let's go. So let's start from this. So what is P of n over 2? It's just the same thing, but here we have n over square root of 2. If we take logarithm, it will just log n minus 1. So this P of n is just 1 divided by log n minus 1. Log base square root of 2 everywhere. Yeah? I'll just omit this square root of 2. It's for all logarithm, it's square root of 2. Okay, so this is the probability of success. Now I need to take 1 minus this. 1 minus this will be... So I need to have log n minus 1 minus 1. Yeah? So it will be log n minus 2. Yeah? Over log n minus 1. So I calculated this part. Now I need to make square of this. So square of this will be log square minus 4 log n plus 4. Yeah. Square of this will be log square minus 2 log n plus 1. Right? So I just calculated this square. Okay, not fast enough. That's almost it. Okay, now I need to calculate 1 minus this. So I need to subtract this denominator I need to subtract this denominator from this denominator, right? So I calculate 1 minus this. So I need to take this minus this. It will be, so log square minus log square is nothing. Now I need minus 2 plus 4, it will be plus 2. And here I have 1 minus 4, it will be minus 3. So I calculated this part. And finally, I need to multiply denominator by 2. So I just multiply this thing by 2. 2 minus 4 plus 2. Huh? Looks fine, right? I think it's good. And now finally I need to, I just simplified this formula, yeah? And now I just need to prove that this is greater or equal than 1 divided by log n. No, I'll multiply this here. I need to prove that 2 log square n minus 3 log n is greater or equal than 2 log square n minus 4 log n plus 2. Now I just eliminate this, move this thing to the left, and I just have that log n is greater or equal to 2. So I can use this, how it's called? How do you call this thing in proof by induction? So you have transition, yeah. So I can use this transition when log n is at least 2. That's fine. So I'll just prove the base for log n equal to 1. So if log n equal to 1, it means I have just small graph, and I'll just prove it that it's true. It's actually probability is 1 when you have a small graph. Now we just make this transition from n over square root of 2 to n. So this transition works for all logarithms starting from 2. Yeah, it's good enough. That's all. Well, you can do it if you want to transition works for all logarithm, you need to add something here. You can add some constant here to make something better here, but it actually even like this is good enough. So this transition works for all logarithms starting from 2. For all logarithms less than 2, you can just prove this as a base case of your induction. It's good enough. Okay. Induction step, thank you. Yeah. Sometimes I forgot how to English. Sorry. That's all. Now the final time complexity. Final time complexity is combined from all these steps. So I have n square log n solution. I need to repeat it log n times to have a good time complexity. And then I repeat it, let's say again 1 over. So this many times to have a probability of error at most epsilon. That's all. So that's the final time complexity. Again, let's just see that it's actually better than everything we did before. So the best algorithm we had before has time complexity like n cube. Yeah. So in the previous algorithm, in the Stoer-Wagner algorithm, we had n iterations. Each time we make all these steps. So the previous algorithm has time complexity something like that. So even if you have Fibonacci heaps, you have time complexity something like that. So even if you have Fibonacci heap, you have still this nm here. So and here you just have n square. So it's better even if you have Fibonacci heap. But it is random. It is independent of edge. No, I calculate this. So I assume that the number of edges is no more than n square. So, okay. Everywhere I assume that number of edges is no more than n square. Yeah, if you have more than n square numbers, then you can do it. Okay. Yeah, that's maybe a problem. You can modify this algorithm to work with. I always assume that I have all weights of the edges are equal to 1. You can modify this algorithm to work in the case when you have weighted edges. How to do it when you have some weights on edges? You just do all the same steps, but when you select random edge, you just apply this probability. So we just select edge at random, and all edges have the same probability. You just need to select the edge with based on their weights. So the heavy edge must have the bigger probability than the light edge. So actually probability should just be linear. How it's called? You need to distribute the probability proportional to the weights of the edges, and if you just do it, then the probability will be what you want. So this algorithm can be easily adopted to the weighted graph as well. You can think about it as an exercise. Just do all the same step and prove that it's still correct. Here you'll something different. So here the probability will be the same. So if you select a random edge and the probabilities are distributed proportionally to the weights of the edges, then probability that you select the edge from the minimal cut is still 2 over n. You can prove it as an exercise. Okay, that's all for today.